Since 2012, we had had such a huge leap forward in the field of artificial vision, and specifically for image recognition. Most of it can be attributed to the introduction of the ImageNet dataset, which is a dataset of 1,000 classes, and each class has 1,000 images, for overall 1 million images. These images are much wider respect to everything we have seen before, like the MNIST, modified MNIST, or the CIFAR dataset. They are 256 pixel in height and 256 pixels in width. And they are color images, so they have 3 channels. So since 2012, we have seen a variety of neural networks that have been trained on this dataset in order to perform image classification. We started in 2012 with the AlexNet architecture, which was the first neural network that was being trained on the ImageNet dataset. Over the course of the last years, we have seen more architectures trained on this task from Google, from Microsoft, from many other institutions. And we achieved better and better accuracy. Here I'm showing you the top 1 accuracy, which is just basically the final prediction of the network. These networks here, they have more and more layers. We have seen that after a specific number of layers, actually these networks couldn't reach better accuracy. And then we have had, therefore, the introduction of the ResNet family, which allows us to fight the vanishing and exploding gradient problem. We have seen other networks like GoogleNet and eNet, efficient network, which have also the aim of minimizing the number of computations, and therefore exploit better their parameters in order to extract information from the input data. As I said, this network add more and more layers in order to achieve better performance in terms of accuracy. We have also to pay attention that there is a very important trade-off between accuracy and computational time or computational burden. So here we have a similar chart where we are going to be representing on the y-axis the accuracy of these networks. So we have on the bottom part the AlexNet architecture and the batch normalized version. As we move towards higher accuracy, we see the batch normalized network in network, and then we have another small cluster of GoogleNet, the efficient network, and the first ResNet network. And then there is another bunch of network. We see that the size of these blobs is proportional to the number of parameters that the network has. So we can see here how, for example, the VGG network compares to some smaller, let's say, ResNet network. They achieve a slightly better performance in terms of accuracy, but they are using many more parameters. So they are less capable of exploiting their learning capabilities. Finally, on the x-axis, we can see the number of operations. And therefore, we can see in the top part how we can trade accuracy for number of operations. So as we increase the number of layers, we are going to perform more and more operations, which is going to be, therefore, taking more time in order to produce one output value. So let's see now how we can use some of these pre-trained networks in PyTorch.